So our next speaker is Matthew Ho from Columbia University. Dr. Ho received his PhD in physics from CMU, studying deep learning for dynamical mass estimation of galaxy clusters. And he's taken 2 postdocs jointly with the Simons collaboration on learning the universe, developing emulators and inference methods for cosmological analysis. One was at the Astrophysics Institute in Paris, and the other at Columbia, where he is now. Go ahead.
Cool. Thank you very much. Hi, everybody. I'm Matt. As was mentioned, today I'm going to be talking about our work in learning the universe, specifically with regards to applying machine learning models to real observational data. But the structure of my talk has changed a little bit upon realizing that not everyone in this room speaks the same language. I'm an observational cosmologist, but I know there's particle physics people, there's machine learning people, there's all sorts of people in this room. So really what I'm going to be trying to address is I have this problem that I want to solve with ML, but I don't know if I trust the ML, right? How do I diagnose what's happening or test it robustly to build faith and build trust in the community that I can then publish the result, right? By the way, this thing on the right is a real cosmological simulation. Are there any people in the room that recognize it? It is the city of Boston. Yeah, it's constrained to evolve exactly like the city of Boston. Yeah. Okay. Yeah. Okay. So I'm going to be a little cheeky, right? And say that this is how you build a universe, right? So I think of computational cosmology as an extension of the culinary arts, right? In that, when we construct a simulation of the universe, we take some ingredients, like some parameters from the Big Bang and inflation, some ingredients of matter, of baryons, of dark energy, and some types of supernovae or types of active galactic nuclei and all sorts of interactions that can happen in a simulation, right? And then I follow a procedure to run a simulation. I combine all the ingredients into a single point, and I inflate. I let that cool for 380,000 years until the universe is transparent. I mix around the dark matter until it looks like a web. I ignite stars. I season with supernovae. I cook until the galaxies start to look red. And then eventually I wait 13.8 billion years for intelligent life to invent telescopes and then blame all their problems on systematics, right? And if you do that right, you'll get telescope observations that look like this on the right. And the reason I like this metaphor a lot is because everyone, just like in culinary arts, people are very opinionated about their recipes and about the correct ways of doing things, and so are cosmologists. So my job as an observational cosmologist is I just read a recipe, and I follow the recipe, right? But what I want to do is I want to take these observations on the right and use them to infer the ingredients that were put into the simulation at the beginning, right? However, unfortunately, just like you can't unbake a cake to find out what went into it, you can't reverse the evolution of the universe to find the ingredients that went into it, right? Okay, so a little bit more concretely, I think about explicit and implicit likelihood inference, right? So I have a simulator, right? In my case, it's a cosmological simulator, but it can be anything, in which sometimes I input some parameters to that simulator and I get out some data. Or I might run that simulator and I might have some things that I can observe, x, and some things that I might not be able to observe, but I might want to measure, theta, right? And my goal with building an inference module is to give my inference module some data x, and then I output the distribution of possible parameters which would be consistent with that observation, right? And there's 2 key distinctions here, right? I can either totally understand my simulator and write down an analytic likelihood of the probability of observing a given x given some parameters, theta. And if I can write that down well, and preferably differentiably, I can run MCMC given some observed data and then measure the distribution of parameters, right? Or, and this is very often the case in cosmology, the likelihood is very hard to write down. It's either extremely complex and nonlinear, or it's really intractably difficult to compute. So a lot of the times we rely on machine learning to emulate that likelihood, right? And the reason I put these two terms here is I'm going to come back to this phrase implicit inference a lot, because you might have heard it before in terms of simulation-based inference or likelihood-free inference, but in our collaboration, we call it implicit likelihood inference. It all means the same thing, right? Okay, so let me give you an example, right? This is how cosmology is done in 2024, right? These are the results from the DESI full shape analysis that was released just last year. And I'm showing on the left the data that we observed, right? So DESI went out and measured the positions and spectroscopic redshifts of all the galaxies on the sky, and then measured how clustered those galaxies are in space, right? And the amplitude of these lines at all these different scales represents how clustered you expect galaxies to be at representative scales, right? Now, the way that we measure cosmology from these lines is I will run a very expensive simulation of the universe, which I put as much physics into it as I can, and I use that expensive simulation to describe for me the mean trend of this line as a function of the parameters I'm interested in measuring, right? And then I run some cheap simulations for which I can run a lot and measure a covariance of this mean for a fixed, usually fixed cosmology. And I put these two ingredients into a simple Gaussian likelihood, and this is an analytic likelihood, and now I can run MCMC to get the constraints shown on the bottom about the amount of matter and the clumpiness of matter in the universe, right? But already you can start to see that, maybe this is not the best approach. Number one, the likelihood is not always Gaussian. Number two, these expensive simulations might not be diverse enough to specify all the behavior that could be happening in these lines. So we can do something better, right? So a couple years ago, this collaboration, the SIMBIG collaboration, produced this analysis with raw simulations. So what they did was they took just a suite of 2,000 expensive simulations and put in all of the physics that they could possibly input to make mock observables of the CMASS South Galactic Cap dataset, one of the datasets that's very similar to DESI, right? And if they could do this, if they could construct a simulation that was realistic enough, they could train a machine learning model to then look at the full field of galaxies, extract as much information as they possibly can, and use that to constrain parameters on up to an order of factor of 2 better than the traditional analysis, right? Now, this is the future, right? Like, this is how we get more information from the limited amount of observational data that we have. However, the problem is that this is the last time this will be done, right? So this SIMBIG analysis was done on a volume of about a gigaparsec, right? But the data that we observed even 10 years ago is on the order of 8 or 27 times the size of the data set that was used for the SIMBIG analysis, right? And then if you want to scale to the data that's coming out now from DESI and Euclid, it's an order of magnitude bigger than that, right? And so if you wanted to run expensive simulations on the volumes that we expect from DESI and Euclid, your simulations would at best scale as n log n. And so if you wanted to repeat the SIMBIG analysis on the DESI and Euclid volume, you need hundreds of millions of CPU hours. And what's even more worrying is 80 petabytes of data stored on file, right? So I can say without a doubt in my mind that this is the last observational sample that will be done with pure raw simulation, right? So this is the spirit of learning the universe, right? Learning the universe is a very broad collaboration of a lot of different people doing a lot of different things, but the general thesis of learning the universe is I want to run some expensive simulations of the evolution of the universe, given some ingredients like dark matter, dark energy, and the initial conditions of the universe, right? I use these expensive simulations to create small volume simulations and mock observables. And then I train machine learning emulators, or as we call them, accelerated forward models, to repeat the steps that were done in the hydrodynamical simulations, but in a much faster way, right? And in doing so, we can scale the very advanced first principles physics to the large volumes that we expect with modern surveys. This is the only way that you can think about doing this, right? And now, we work on a lot of different projects, some of which are not machine learning related at all, But what I'm going to talk about is the problems that we face when we do this, right? So I've borrowed Alex's circle of doom plot to say that, all of these problems like domain shift and uncertainty estimation and interpretability get even harder when we add another machine learning model in the mix, right? I'm no longer just using my ML to do inference. Instead, I'm using it to generate my training data that I then want to train on and produce predictions, right? And just like we do in regular cosmology, machine learning models are approximators, right? They make approximations, they make assumptions, and then they approximate physics. So how do you know if those assumptions are valid, and how do you know if the physics being approximated is correct? So I lead the implicit likelihood inference group in the Learning the Universe collaboration, right? And the main engine by which we do a lot of our tests is with this code called the LTU implicit likelihood inference pipeline, right? All it is a series of modules, routines, validation metrics, et cetera, which turn training data into posterior constraints, right? And we tried to make it all in one. We included everything that you might need to do your first machine learning inference in astronomy, right? We include all different libraries of neural architectures, neural flows. We include model ensembling. We include best practices. We include every type of embedding network that you might want to use and examples for how to use them. And the best part of this code is that you can run a full inference pipeline in just about 5 lines of code. Clearly, we can do a lot more. The code can get a lot more complicated than that. But this tool was initially developed as an internal thing for our use, for applications to things that we develop. But then we decided to make it public, and it actually seems to have gotten quite a bit of traction in the field, right? So this code is public. Anyone can use it. You can start doing this in just about 10 minutes. And if I had known this was going to be public, I would have given it a better name than L2ILI. This is like my number one career regret. Okay, so some of the things you can do, right? You can plot contour plots, like given some posterior samples, I can measure the 68, 95 percentile confidence intervals, and I can plot that with respect to the true, right? I can do my true versus predicted plots, which we've all seen a lot, right? I can also do my posterior coverage plots, right? So these plots on the right, like PP plots and like TARP plots, basically measure if I report with my machine learning model that these are the 68 percentile intervals, then 68% of the time, my true values will fall within that interval, right? And this is something you can test on a validation set or a test set, right? So this is how you know when you quote uncertainty error bars in your paper that you're correct, right? So other things you can do. The code is extremely modular and really easy to use, so you can test basically every flow architecture that you could possibly want. These are only a few, and measure their validation, loss as a function of bias, and find the best ones for your use case, right? So this was done with the Optuna hyperparameter search. You can also benchmark all of these methods against each other to find which ones are the best ones, right? So these are each 3 different plots of the 3 different flavors of simulation-based inference, or implicit likelihood inference, where on the x-axis is the number of training simulations I used to train my model, and on the y-axis, this is an error metric, right? So the lower that these numbers are, the better, the less the error. And what you can see from our internal tests are that neural posterior estimation and neural likelihood estimation do really well, but vanilla neural ratio estimation does really bad. And this is a really important plot to make, especially for people that don't have time to do all this testing themselves. Okay? Now, there's been a lot of applications of this code in the field, but I just wanted to highlight one because I know there are particle physicists in the room. So one work that we have coming up is through the GRAND collaboration, where we are trying to measure the angle of incidence of a ultra-high energy cosmic ray on the field of GRAND radio telescopes that are in China, right? With LTU-ILI, what we've built is a graph neural network which parses the activation times and energies that each of these radio telescopes observe, and is capable of producing constraining power on the angle of incidence to a sub-degree precision, right? Which, compared to baselines of every other model in the grand collaboration is about 2 degrees, is a significant improvement, right? But I don't mean to show this because like everyone should go and use this code. I mean to show this because if anyone in this room has tried to use an SBI package to do graph neural networks or to implement a customizable loss, I'm sure you've spent many sleepless nights doing it, right? What I'm presenting to you is a code that does this and is extremely transparent that you can go in and modify it yourself to produce research like this, right? Okay, now I want to talk about what I use this for, right? And specifically, I want to talk about how do we know when we've discovered something using a machine learning model, right? And typically the way that goes is your model works and you don't know why, right? Your initial intuition suggests that it shouldn't work, and then it works, right? So let me give you an example. As a part of the Learning the Universe collaboration, we run hydrodynamical simulations, right? We have several members which are involved with the CAMELS collaboration, which run various suites of cosmological simulations which implement various models of astrophysical feedback, right? Here are 4 different simulations evolving through time and showing how the different models of astrophysical feedback affect the clustering of matter and the distribution and temperature of gas, right? So we run lots of simulations like these, which are relatively small volume, and then we try to make them look realistic. So Chris Lovell, who is a close collaborator of mine, took these CAMEL simulations, about on the order of 10,000 hydrodynamical simulations, and did all the stuff that we know how to do, which is run stellar population synthesis, apply galaxy dust models, and measure rest band photometry of each galaxy in the CAMEL simulation, right? So calling back to Peter's talk yesterday, we know how to do that, and it is computationally tractable, right? So why would we use machine learning to emulate it, right? So what Chris has done is measured the brightness and the color of every galaxy you'd expect to see in the CAMEL simulation. And then what we can plot is the luminosity function, or basically a histogram of the brightnesses of each of these galaxies, and a histogram of the colors of each of these galaxies, and observe the differences between the different simulations. But Chris and I were sitting one day at the LTU meeting, and we were like, what if we just threw this at machine learning and saw what happened, right? Specifically, what if we took these distributions of brightnesses and these distribution of colors and asked it to infer the cosmologies that the simulations were constructed from, right? So let me give you an intuition check, right? Who thinks this is going to work? No one? Good. Right? I didn't think so either, right? Because usually you constrain these parameters with clustering statistics, with dynamics, right? You observe the positions of galaxies, and that tells you how much dark matter there is, and the influence of that dark matter on the motion of galaxies, right? So if I'm only measuring a small patch of the sky, about 25 megaparsecs, how could I possibly know anything about the amount of matter in the universe, in the whole universe, or the clumpiness of that matter in the whole universe, or the strength of supernovae, or the strength of AGN? Well, it turns out you do pretty well, right? So we didn't expect this, okay? So what I'm showing is true versus predicted plots for all of these parameters. And what you can see is we get very tight constraints on omega matter. We get very tight constraints on the feedback of supernova, the strength of explosions of supernova in galaxies. And we also get reasonably tight constraints on sigma 8, which is the clumpiness of matter. And that was particularly surprising, right? You could imagine if I simply told you the total number of galaxies in a given co-moving volume, that would correlate with the amount of matter in that co-moving volume, right? That makes sense, right? So it makes sense to infer omega matter to some extent, right? But how clumpy that matter is has to first go through the formation of the galaxy in its accumulation of matter from its environment, and then that has to get forwarded to the photometry of the galaxy, which we didn't understand at all, right? So what we did was we did basically an ablation study of what happens when we turn this on and turn this off and see what the constraints get. What we found was that, number one, luminosity functions alone was insufficient to constrain omega matter and sigma 8 tightly. and colors alone were good, but not great at constraining omega matter and sigma 8. These are stacked posteriors, so the higher this peak is, the more constraining power that we have. And what we found was we needed a combination of both the brightness of the galaxies and the luminosity and the colors of the galaxies in order to get good constraining power. Similarly, we needed to observe multiple galaxies at multiple redshifts, right? So if we only took galaxies at a single redshift snapshot at a single place in time, we didn't really get good constraints. But if we tracked galaxies, or we tracked populations of galaxies as a function of time, then we got some good constraints, right? Which tells us the information is coming from the evolution of these galaxies, right? Not from their redshift 0 properties. And what's even more compelling is when we looked at the data in a different light. So what I'm showing here is the look-back time of formation of the galaxy as a function of sigma 8, as well as the metallicity of the galaxy as a function of sigma 8. We see that at higher sigma 8s, so in universes which are more clumpy, the galaxies that we observe in our catalog formed earlier, right? The look-back time is larger, right? If the sigma 8 was smaller, then they formed later, right? So the scientific explanation we can come up from the serendipitous discovery was that in high sigma 8 universes, galaxies preferentially form earlier because they are in clumpier environments. And as a result, they have more time to turn red and generate high metallicities. And as a result, you can trace back that information all the way to cosmology. Right? This is a probe that no one has investigated before, right? And by just making machine learning tools available to the community, we're able to try things that we've never tried before and actually come up with some interesting discoveries. So here's an even more bizarre case, right? Several people in the audience might have heard of this paper, Cosmology with One Galaxy. This paper was before L2ILI was developed, so it wasn't done with L2ILI, but the results that we're going to show are. So this paper took individual galaxies in each of these camel simulations and tried to infer cosmology, right? So I'm no longer looking at aggregate properties of luminosities or colors. Instead, I'm looking at a single galaxy's mass, a single galaxy's metallicity, a single galaxy's spin, a single galaxy's stellar mass, et cetera, et cetera. I'm plugging that into a fully connected machine learning model and asking it to predict omega matter and sigma 8. And just by measuring a single galaxy, we can get constraints on omega matter, right? Which is ridiculous, right? That just means if I just looked at Andromeda and I measured it really, really carefully, I could measure the total matter in the whole universe, right? Which doesn't make a lot of sense, right? So this baffled us for a very long time, and we figured out that a lot of these properties overlap with other ones. So the machine learning model has to be taking advantage of correlations of this information, right? Which means that the galaxies at different omega matter have to live on different manifolds in this very high dimensional space, right? So we had developed this, this autoencoder framework called information ordered bottlenecks, right? This is an autoencoder in which you input some data and ask it to get the same data out at the other side, right? But the key behind this model is that during training at the bottleneck layer, we randomly close off some of the nodes to prevent information from traveling left to right, right? But we do it in this hierarchical scheme, which says that, if the fifth node is closed, then the sixth node is closed. If the fourth node is closed, then the fifth and the sixth nodes are closed, right? Such that if you construct a loss function, which is a summation of all of these various conditions, your neural network will notice that the most important information, the most reliable neural pathway is the one at the top. The second most reliable pathway is the second one, the third one, etc. So what it will try to do is compress all of your information into as many of the top nodes as you possibly can, right? And this is going to push me over time, but this is my favorite example in the world. This is my dog, Andre, right? And when I was living in Paris, I missed him very much, so I asked DALL-E to make me more pictures of my dog, Andre. And then what I did was I attached this bottleneck model to try to threshold the amount of information that could move from the left to the right, to try to understand how DALL-E decomposed information. So when I close the bottleneck all the way, this is at test time, When I close the bottleneck out all the way, I input my image of my dog, I output something that's totally random, right? When I open one node, it's still totally random because there's no information. When I open 3 nodes, I start to get some grass in the background, but still it's not a dog. When I open 5 nodes, I get some weird fluffy thing, but it's not my dog. When I open 10 nodes, then I get a dog, but I don't know who that guy is, and he's sitting in a field of grass. So I'm starting to get objects, I'm starting to get information. Then I start to get physicality, right? So I have the dog looking at the camera now, but there's still some weird things going on in the background. So again, I'm thresholding information through this many nodes. I start to get orientation, so the dog is now sitting at 30 nodes, right? So I can produce that information with 30 nodes, right? Then I start to get colors, so now the color of this dog starts to look like my dog. And what's even interesting is around 70 nodes, then I get background information, right? So it focused on the thing in the foreground first, and now in the background, I'm starting to see that the dog is sitting on a hill, and there's a bunch of dead trees in the background. Then I see some hills in the background, and I see my dog's collar. And then at the end, at 150 nodes, I see lighting, right? So I start to see the least important feature that this model thinks, it's the lighting of the scene, right? And then I can go further, I see buildings in the background, et cetera, and then I get to my dog, right? So what this is trying to do is show that I only need X latent variables to describe orientation, or to describe colors, or backgrounds, et cetera, right? We can do the same thing with astrophysics. So Amanda Liu, who's a PhD student at Columbia, did this analysis using the properties of cosmology with one galaxy. Basically, she tried to auto-encode these properties, but did it as a function of the bottleneck width, right? And what she found was that at around 7 nodes open, the amount of information that our model uses to describe all of these parameters saturates, right? Which means that with just 7 latent parameters, I can describe the distribution of 16 latent parameters over here, right? Now, what's even more compelling is those manifolds that it learns, the 7-dimensional manifold that it's learning in a 16-dimensional space, is unique to individual cosmologies, right? If I train my autoencoder to find a manifold at, let's say, omega matter of 0.3, and I try to test my autoencoder at omega matter of, let's say, 0.4, I get reconstruction error, right? I get reconstruction error when I go below that omega matter as well, right? Which means that this manifold is ideal for a very specific cosmology. But for other types of things, like if I change sigma 8 or if I change the strength of AGN, the manifold fits perfectly everywhere, right? So the explanation behind cosmology with one galaxy is the following, that when I run a simulation, the galaxies live on some lower dimensional manifold in this high dimensional space. And then if I want to change omega matter, the manifold itself will change, right? So what the neural network is doing when it predicts omega matter is it figures out which manifold the galaxy is sitting on, and then it predicts what omega matter corresponds to that manifold, right? However, if I were to change other parameters besides omega matter, like sigma 8, all I do is I move the distribution of my galaxies to a different region of that manifold, right? So I'm learning things about this development of galaxy galaxy properties in a hydrodynamical simulation. Okay, so with just a couple minutes left, I'm going to talk to you about what I work on, or at least what's my day job, right? Which is trying to productionize this work to large surveys. I'm calling back to the thing I described at the very beginning, right? When you create these mock observables of galaxies on the sky, there's a lot of steps involved, right? I run a simulation. The simulation gives me halos in space, dark matter halos in space. I populate those dark matter halos in space with galaxies. I position those galaxies on a light cone. I cut out various masks and stuff. And then I measure things like 2-point correlation functions. And then I compare things to the observational data, right? But the most expensive part of this pipeline is running the dark matter only simulation, right? So what we did in LTU is try to show that you can beat this complexity with emulators. So we have this emulator called the CHARM emulator, creating halos with autoregressive multi-stage networks, in which all we've done is replace the expensive high-resolution simulation with a cheap, low-resolution particle mesh simulation. and then replace the finding of halos with a emulator model. This is a hierarchical normalizing flow. We don't have to go into the details, but the point is I input a low-resolution dark matter field, and I output a catalog of positions, velocities, masses, and concentrations. Right? All the things that I need to create galaxies, which are all the things I need to create Machs. Right? And the key is that this is 1,000 times faster than running the expensive simulation. However, you pay the price by relying on the fact that this is a field-level emulator, which you might not trust. Right? So all the work that I'm going to talk about is all the things that I do to trust this model. Right? So what I will do is I will construct a Mach with this emulator. Right? I will construct galaxies on the sky, and then from these galaxies on the sky, I then measure things like the 2-point correlation function, the 3-point correlation function, wavelets, etc. I plug that into the L2-ILI pipeline that I described before, which does all the best practices, does all the normalizing flows, does all my validation metrics, and then the goal is to output constraints on cosmology and galaxy parameters, which would, again, tell me the ingredients that went into my recipe. Right? So, train and test on the same simulation, right? So the CHARM emulator was trained on this suite of simulations, the Quixote suite of simulations, right? So I would expect it to do well in predicting on the Quixote suite of simulations. So what I'm showing here is constraining power of including all of the 2-point statistics that I typically might use, as well as the 3-point statistics. And then I'm using that to predict omega matter and sigma 8 and a bunch of other parameters that I don't really have great constraining power on because this is not the ideal observable for those, right? But what I can show is that, true follows predicted across the parameters that I have constraining power on, and that when I quote error bars, the error bars are actually what is present in the data, right? If I tell you 68% of the time you should expect to see the real universe in this range, then actually you get 68% of the real universe in that range, right? But this is boring. I'm going to go quick on this because this is just train and test on the same thing, right? Now, what we did was we know observational cosmologists are skeptical. So we wrote down every assumption that we made when we constructed these Machs, and then we tested them individually, right? The first assumption is that we scale with volume, right? So what I'm showing here is on the x-axis is the volume of various surveys, right? So, the number of galaxies that I observe. And on the y-axis is constraining power on the amount of dark matter in the universe and the clumpiness of dark matter in the universe, right? So you'd expect by the law of large numbers for the constraining power on any estimate to go as roughly 1 over the square root of volume. And indeed, we see that, right? So what I'm showing here is for a variety of different probes, like the 2-point statistics and the 3-point statistics, the constraining power for a survey of a volume of 1 gigaparsec or of 2 cubed gigaparsecs or of 3 cubed gigaparsecs. So roughly, we see the scaling that we might expect, except for that, right? So one condition in which we don't see the scaling we might expect. Now, there are observational cosmologists in the room who probably know where this is going, which is that the parameters, this probe, the power spectrum monopole, produces constraints on sigma 8, which are highly degenerate with another unconstrained parameter, log m min, which governs our galaxy populations, right? And so you can't disentangle constraints on sigma 8 or log m min. Instead, you can kind of just shrink this banana and make it tighter, right? But as soon as you look at anisotropic probes, like the power spectrum quadrupole or the 3-point statistics, then you see the scaling that you might expect, right? So these are the advantages that we want, right? Similarly, we test all the different assumptions, like using different test simulations at different volumes, with different gravity solvers, with different halo finders, with different mass definitions, everything that you could think to algorithmically change. And we show that if we train on our model and test on an out-of-distribution model, that we get good true versus predicted plots, right? Even for our most stringent case. Similarly, if you don't trust, let's say, HOD models, and you do trust very advanced galaxy models like semi-analytic models, we train and then test on the Millennium TNG light cone, which is a full high-resolution n-body simulation which uses very advanced galaxy models, right? And the key behind our approach is creating simulations is cheap for us. If I make this constraint, I can create a digital twin of this universe in minutes with my emulator approach, if my constraints are valid. Okay, so I'm just going to end on this plot here. All right, so I've talked about developing observational inference with field-level emulators. I've tried to convince you that it's absolutely necessary if we want to look at the large surveys that are coming right now. If you want to do this, you have to write down and test each one of your assumptions. And we are working now on the unblinding process of this analysis, and we'll hopefully have cosmological constraints by the end of the summer. And I want to end on this plot from 2015. This is Google's MLOps group, right? Which says the amount of work necessary to serve ML to clients, right? The actual ML code is just this little box here. But all the work that we put in to get people, to convince people this is accurate, to make it available, to make it reproducible, is all of this work on the outside. So I would encourage people to value that work, to spend a lot of time doing that work, and make this work very trustworthy to the audience. Thank you very much.
Great, thank you. Are there questions?
Hey, great stuff. I really like the fact that you emphasize the need for validation for these things. And I would like to kind of know whether you have checked for the things that are sort of cosmology with one galaxy, which requires things that you can't directly measure. And then if you try to do it with observables like photometry or spectroscopy, you're kind of involving another model on top of the SAMs and on top of the simulations. You use now kind of a model like SPS, for instance, to produce these things. Absolutely. They all make assumptions, and we know those assumptions to be quite incorrect. It depends on which regime you're in.
Right.
So have you checked how much, like, which of the things you can reliably say by sort of varying the models and seeing kind of which of the things are sort of stable and which of the sort of cosmological conclusions are therefore kind of inferable in the way that you indicated?
Yeah, so specifically with respect to the cosmology with one galaxy, we have not been as exhaustive. That was more of like we didn't understand how this could work even in a simulation, right? With the luminosity and color distributions, we did play with that. So what we found was that when we included observational noise, in fact, of a survey of a very small volume, our constraints on sigma 8 were unfortunately wiped out, right? Because you don't have the statistics to appropriately characterize those things. Also, that paper assumed a fixed dust model, which we know is highly uncertain. So we're actually working on a follow-up of that paper where we vary the dust model as well as the cosmologies. And we do see, again, in the idealized case, still constraints on sigma 8. Now, those constraints are slightly degenerate with dust model and other properties. However, I'm thinking exactly the same way, which is that we are slowly building up the realism. We will produce some findings, but then as we build up the realism, some constraints will go away, or we might get other constraints.
Hi, Matt. Thank you. This was really cool. I wanted to ask again about the cosmology with one galaxy example and the information ordered bottleneck. And so I guess I'm wondering if you can clarify what new things you learned either about the astrophysics or cosmology with that example, where I guess you had like some 16 parameters and you found you only needed 7. So did that tell you something new about degenerate information in your astrophysical parameters that you didn't expect, or covariance with omega matter that you didn't expect?
Yeah, so we did, this is escaping me because this was a year or so ago, but we did basically, we figured out what the shape of the manifold looked like, right? Which would tell you, for a fixed omega matter, how do we expect certain galaxy properties to be, correlated with other galaxy properties? And that largely made sense, right? Similar to the arguments that we made with the luminosity functions, right? Changing omega matter changed the environment that the galaxy formed in, and therefore might change it to be preferentially older or preferentially younger. The specifics, I'll have to point you to the paper, but that's a type of analysis that we could do. The reason I didn't present that here is that's also not super robust, right? Like, I mean, there are correlations, but they're not like super statistically significant correlations.
Yeah, that makes sense. Could you imagine if you wanted to make it more rigorous doing this across many single galaxies and camels? Or was that?
Yeah. I mean, well, one work I think that's actually actively going on now is trying to robustify that cosmology with one galaxy across different simulations. So you have, 5, 6 times as much training data. However, you have to sacrifice the fact that you have to marginalize over different astrophysical prescriptions. So that's being worked on, I think, by Young-Suk Cho at Columbia, and hopefully that'll come out later this year.
Yeah, that makes sense. Thanks.
Hi, Matt. Thanks a lot for the nice talk. Yeah, so I have a few questions. So one of them, so first of all, do you know if you did the same with a Gaussian likelihood where you just learn the covariance, do you know whether you outperform, for this analysis that is PK and BK, whether you outperform it with SBI or not?
Yeah, so that's not on this plot that I showed here. But the context is that SIMBIG outperformed the classical 2-point and 3-point analysis in producing these kind of amounts of constraining power, right? So
sure, yeah. I'm just like, you only need the flow machinery, right? If you're if your likelihood isn't Gaussian,
right,
otherwise you're doing better with learning the covariance matrix. Right. And I just want to know whether if this is the case or not.
Yeah, that makes a lot of sense. So basically, you're saying is use these simulations that we're making to estimate mu and sigma, and then do the classical analysis. We should do that. We haven't done that ourselves, but that would be a really interesting comparison.
Okay, thanks. And another question. So what is if I understand right, the difference of this to SIMBIG is that your forward model is not the Kikoto simulations, but it's this emulator-based framework.
Exactly.
Can you say again what's in the emulator? What is the forward model?
Yeah, so the forward model is, I'm going to take a low-resolution particle mesh simulation, which I can run on a very large volume, and correlate large-scale structure. And then I'm going to leave the small-scale structure to this emulator, right? So I'm basically conditioning on the density and velocity fields of this low-resolution particle mesh simulation, and I'm using that to position halos in voxels.
Okay.
Yeah.
And so I guess a worry here is how to, if you do the same with the EFT analysis, then you do get this set of bias parameters.
Yeah.
And I think it's not clear that this model that is a dark matter particle mesh with a halo patch up on top of it, that this would have the same degree of freedoms, the same as the EFT analysis. Do you have some thoughts about that?
Yeah, so I mean that was something that we were thinking about as well, right? Which is that here we're only really testing the Kmax of 0.4, which for the most part I think EFT can handle, maybe 0.3 or something like that, right? However, we are using the bispectrum as a probe up to Kmax of 0.4, which from my understanding EFT struggles more with, especially to high K. So I would be very interested to do an exhaustive comparison of the two and to see basically if you can, abstractify this emulator with the bias parameters in EFT and if they are effectively equivalent, or there's additional nonlinear terms that this model is picking up that EFT isn't, that allows us to model the higher K modes, the more nonlinear modes.
Thanks.
Thanks.
One last question before the break. Great. Well, let's thank Matt again for a great talk.